So good morning, friends. We'll start today damage mechanism affecting fixed equipment in refinery industry. ANSI API Recommended Practice 571, third edition, March 2020. This is the latest one. We have terms and definition. Amine stress corrosion cracking, atmospheric corrosion cracking, and boiler water and steam condensate corrosion. So let us see these three. Brittle fracture is not there this time. To see here, so brittle fracture is not there. So let us see first how much we can see from there. Terms and definitions. Will not go too much to it. Only austenitic see small. What is the difference between? The term refers to as a type of metallurgical structure, austenite, normally found in 300 series stainless steel and nickel-based alloys. These materials have face-centered cubic crystallographic structure and are generally non-magnetic because austenite in the room temperature. Because of nickel, so not chromium. Chromium is not stabilizer for austenite. Nickel is stabilizer for austenite. So there is 347H. L and H suffixes refer to. So there are 304, 304L, 304H, 309, 310, 316, 316L. All 3 series is austenitic and non-magnetic. The L and H suffixes refers to control ranges of lower and high carbon content. Less than 0.06 for L and more than that FFH. So carbon steel, Duplex stainless steel, a family of stainless steels that contains mixed austenite and ferritic structure, including alloys 2205, 2304, 2507, and welds of 300 series SS may also be exhibit a duplex structure. These are really used for high corrosive medium or erosive medium, you can say. High strength low alloy steel, HSLA, a family of carbon steels in which higher strength levels are achieved by addition of moderate amount of alloying elements such as titanium, vanadium, niobium, amounts to less than 0.1%. They can be more sensitive to cracking during fabrication from hydrogen enrichment, delayed cracking, also known as underbeat cracking. Low alloy steel 1.25 CR 0.5 MO, 2.25 CR 1 MO, 5 CR 0.5 MO, 9 CR 1 MO, 0.5 MO, 1 CR 0.5 MO. All are low alloy steels. Nickel based alloys, a greater than 30% nickel, 200, 400, K 500, 800H, 825, 600, 600H. So all are these alloys. And stainless steel. So more than at least 10.5% chromium. That is called stainless steel. They are ferritic, austenitic, and martensitic, and duplex. Let us see then amine stress corrosion cracking. Description of damage. Amine stress corrosion or amine cracking is the cracking of steels under the combined action of tensile stress and an aqueous alkaline solution used to remove, absorb H2S or CO2 and their mixtures from various gas and liquid hydrocarbon streams. Amine cracking is a form of alkaline stress corrosion cracking, ASCC. It is most often found at an adjacent or non-post weld heat-treated non-PWST carbon steel welds or in highly cold work parts. These are two conditions for amine cracking with amine. So affected materials, carbon steel and low alloy steel. Critical factors. What are the critical factors? Critical factors are the level of tensile stress, the type of amine and temperature. Increasing stress level increases the likelihood and severity of cracking. Cracking is most often associated with high residual stresses from welding or cold working that have not been removed by effective stress relieving heat treatment. Cracking is more likely to occur in MEA, DEA surveys, but also found in most amines, including MDEA or DIPA, DIPA, ADIP. So increasing temperature increases the likelihood of severity of cracking. However, cracking has been reported down to ambient temperatures with some amines, MEA in particular, that is amine. Amine cracking is most often associated with lean amines. So if it is very small amine, then you have crack. Where a solution of amine and water is used, the pure alkalamine doesn't cause cracking. In rich amine service in H2S removal system, the H2S helps to form iron sulfide FeS film on the steel surface that helps impede amine stress corrosion cracking. Cracking in rich amine service is most often associated with wet H2S. So it is due to H2S only. So cracking can occur in non-PWSD piping, PWSD piping and equipment as the result of exposure to steam out and to short-term amine carryover. This is another reason PWSD stress relief is now commonly recommended regardless of operating temperature. Appearance and morphology of damage. Amine stress corrosion cracks initiate on the process side surface piping and equipment primarily on welds. Cracks can appear in the haze and or the weld metal, but are most often found in the high residual stress zone, which is typically beyond the metallurgical edge, about a tenth of an inch or more, several millimeters from the weld. Cracking typically developed parallel to the weld, and there may be multiple parallel cracks in the weld metal. The cracks are either longitudinal or transverse to the weld. A Saturn nozzle, the cracks are in radial base metal. They fan out from the bore. At satin nozzle, the cracks are usually parallel to the weld. Prevention and mitigation. The recommended minimum stress relief temperature is 1175 degrees plus minus 25 degrees Fahrenheit or 635 plus minus 15 degrees centigrade. Thoroughly water wash non-PWSD carbon steel piping and equipment prior to welding. heat treatment or steam out. Inspection and monitoring. Wet fluorescent magnetic particle testing, WFMT. Alternating current field measurement, SCFM, and eddy current testing, ECT, can be effective technique to detect these surface breaking cracks. Proper surface preparation by grid blasting, high pressure water blasting, flapper well abrasive grinding, or other methods is required to remove scale and contaminants. The method of surface preparation is depend upon the specific technique. Angle beam shear wave ultrasonic testing SWUT and phased array ultrasonic testing PAUT. Ultrasonic techniques can be effective to detect the size of cracks and would be method typically used in piping. However, caution must be exercised when the interpreting results of piping welds that have not previously been inspected. With an angle beam UT, SWUT or PAUT, as it may be difficult to distinguish SCC from original fabrication flaws. SWUT and PAUT can also be used to periodically monitor crack growth. Liquid penetrant testing PT may be used but should not be the only means of detection. PT may not be effective in finding tight cracks because the cracks are oxide filled. Acoustic emission testing AET can be used for locating cracks and monitoring crack growth. There are some pictures, a photomicrograph of a cross section of weld and non-PWST carbon steel piping showing amine stress corrosion cracking in the vicinity of piping weld magnification 6x, and then radial amine SCC cracks emanating from the bore of a nozzle. In a rich amine reboiler exchanger. These are higher magnification view of crack tip in figure is 3.3.1, 3-3-1, magnification 200x from API 945, and then photomicrograph of a cross section of carbon steel piping weld showing amine SCC in a section of the line from MEA observer column normally operated at 100 degrees Fahrenheit, 38 degrees centigrade, magnification 6x from API 945. A higher magnification view of the cracks in figure 3.3-3-4 illustrates the intergranular nature of the cracking, magnification 200x. Cracking initiated on ID because the process side amine SCC developed on the inside diameter ID beneath the arc strike. On the outside diameter OD of a 3-inch line in 20% MEA. The original line was PWST during the original fabrication but not the arc strike. Leaks occurred after 30 years of service. Okay, after that we go for atmospheric corrosion. Description and damage. Corrosion that occurs from moisture associated with atmospheric conditions, marine environment, and most polluted industrial environments with airborne contaminants are the most severe. Dry rural environment cause very little corrosion. Affected materials: carbon steel, low alloy steels, and copper alloyed aluminum. Critical factors: why this happens. The physical location of the plant: industrial, marine, urban, rural. The amount of moisture, humidity, rainfall typically present, or presence of cooling tower mist. The presence of salts, sulfur compounds, dirt, other contaminants in the air, chloride, H2S, fly ash, and other airborne contaminants from cooling tower, and wet gas scrubber drift. Orientation to the prevailing wind or rain. Corrosion rates increase with temperature up to 250 degrees Fahrenheit. Above 250 degrees Fahrenheit, surfaces are usually too dry for corrosion to occur except under insulation. Design that trap water or moisture in crevices or other configuration most prone to attack. Marine environment can cause very corrosive, about 2 mpy, 2 mils per year. As are industrial environment that contain acids or sulfur compounds. That can form acids about 5 mpy or 10 mpy. The inland locations exposed to moderate amount of precipitation or humidity are considered moderately corrosive environment, about 1 mpy to 3 mpy. Dry rural environment usually have a very low corrosion rates, less than 1 mpy. Bird dropping can also cause accelerated corrosion and unsightly stains. Affected units or equipment: unpainted insulated carbon steel and low alloy steel piping and equipment operating below 250 degrees Fahrenheit, 120 degrees centigrade, where moisture can contact the surface. Uninsulated carbon and low alloy steel equipment with deteriorated paint coating. Equipment may be susceptible if cycles between ambient and higher or lower operating temperatures. Bimetallic connections such as copper to aluminum electrical connections. The attack will be general or localized depending on the condition of the coating, if any, and whether or the lot of moisture is trapped, whether or not the moisture is trapped. If there is no coating, corrosion or loss of thickness can be more general and widespread. Localized coating failures will promote localized corrosion. Metal loss may not be visually evident, although normally a distinctive iron rust, red rust scale form as shown in figure 3-1, 8-1. Prevention and mitigation. Paints or coatings are normally applied to otherwise unprotected equipment to prevent atmospheric corrosion. Surface preparation and proper coating applications are critical for long-term protection in corrosive environment. Inspection and monitoring. BT includes direct, insight, line of sight, and indirect method using camera, mirror, laser scanning, and or structured white light imaging with pit gauges. Or nowadays robotic. UT can also include technique like straight beam or angle beam, SWUT, PAUT, to directly measure remaining wall thickness of screening technique using EMAT or GWT. guided web testing. RT may include traditional film-based digital computed radiography media and may incorporate techniques such as contact or profiled RT as well as open system imaging. ECT may include a screening technique such as pulse steady current. The related mechanisms, corrosion under insulation, CUI, 3.2.2, 3.2 to 22. The concentration cell touch point corrosion, 3.19. So there is one picture, atmospheric corrosion of an LPG line in close proximity to a cooling tower. Then we have boiler water and steam condensate corrosion. Okay, we'll stop here and restart.